Hello and welcome to lecture 31 of the course Theory of Computation. So far we have seen Turing machines, and we saw the multi-tape version, and then we saw the non-deterministic variant of the Turing machine. In this lecture we will start by seeing the equivalence of the non-deterministic and the deterministic Turing machine model. Clearly, non-deterministic Turing machine has access to seemingly more powers, right? So anything a deterministic Turing machine can do, a non-deterministic Turing machine can also do, in the sense that a deterministic Turing machine can only make the next step is decided once we fix the state and the symbol that is being read. Whereas a non-deterministic Turing machine may have 0 options, 1 option or more options. So since one option is also a possibility, which means that a deterministic Turing machine itself can be viewed as a non-deterministic Turing machine. So clearly, non-deterministic Turing machines are at least as powerful as deterministic Turing machine. So what we are going to show here is that anything a non-deterministic Turing machine can do, a deterministic Turing machine can also do. Meaning, if a language can be recognized by a non-deterministic Turing machine, there is a deterministic Turing machine that recognizes the same language. So in terms of the class of languages recognized, they are the same, non-deterministic as well as deterministic Turing machines. So there are other things like the time it takes may differ from non-deterministic to deterministic. But for now, we are not focusing on the resources used. All that we are caring about is whether there is a equivalent deterministic Turing machine given a non-deterministic Turing machine. And this theorem says that there is one always, right? So the key thing in the non-deterministic Turing machine is that we have possibly multiple options for the at each stage. And what we are looking for is there an accepting configuration that can be reached from the starting configuration. So there is a tree that is formed, the computation tree, and you want to know whether there is some accepting configuration that can be reached starting from the starting configuration somewhere in this tree, right? So the answer is not that difficult, right? So it's a tree, and you may have seen if you learn data structures, you may have seen or algorithms, you may have seen graph traversal approaches. So how to traverse a tree. So two standard approaches are depth first search and breadth first search. So in a depth first search, you start from the root of the tree and then go all the way deeply to the end of a path, right? And once you reach the bottom of the path, you retract back and then you try to go the next path and so on, right? The problem with this approach in depth first search is that the first path that you try to go through, or one of the paths that you try to go through, may be an infinite path, right? So it may be an unending path, and you may just get stuck on that path, right? So you will never be able to get back and try some other paths, and perhaps the accepting computation is in one of those paths, right? So this is an issue with depth first search, right? So we may get stuck on an infinite path. Whereas breadth first search, what we do is we first go level by level. So we first try to go through all the first level, then the second level points, right, in the tree, and then the third level points in the tree, right, and so on. So you go level by level. So you cannot get stuck on an infinite path because you are not going deep. You are just going to the first level, then the second level, then the third level, and so on, right? So that's why breadth first search works, right? And one comment that is here, right? So so breadth first search works, and finally, if there is some accepting path somewhere, so you will encounter the accepting path whichever happens the earliest. And once you see the accepting path, you can accept, right? Because that's what we need to do. To accept the computation, you just need to find one accepting path, right? One point I want to mention here is that this computation tree, we have been talking about this computation tree, right? So it is not like we build this entire tree, because this entire tree itself is so huge. Even if the time taken is t, the branching factor of this tree could be like big. It could be like, let's say it is b. Then that means that we could have b power t possible paths starting from the root node to the leaf nodes, and that's a huge number. So we will not be constructing this computation tree explicitly. Rather, what we will do is we will see, if we are at a configuration, we will see what are the next possibilities, and then we will. So if we are at this configuration, right? If we are at this configuration, we'll see, we'll calculate these three successor possibilities, and then let's say we come to this configuration, right? So this one, the middle one, and then again we'll calculate the successor configurations there, and so on. So we will do it on the go. We will not explicitly construct this graph and keep the and maintain the adjacency or anything like that, right? So this will be an implicit graph, right? So let's try to see what is the process again. So we have a kind of explained in a very high level manner. So the idea is to do breadth first search. So starting from the root node, then the nodes at level 1, then the nodes at level 2, right? Then the nodes at level 3, and so on, right? Finally, whenever we get an accepting computation, we accept and stop the computation, right? So one assumption is that once the machine is fixed, the rules are fixed. Let B be the branching factor, right? So maybe I'll use, so B be the branching factor, which is the max number of children of any node. In other words, it's the maximum number of successor configurations that follows any given configuration, right? So this is entirely dependent on the Turing machine alone and is independent of the input that is given, right? So let B be the maximum number of children possible for any configuration, or the successors possible for any configuration. So at the 0th level we go to the root, then the children of the root, that is, I am labeling it 1, 2 up to B. So the reason is this, so there is a root, and let's say 1, 2, 3, and let's say B, and let's say the node 1 has, let's say, 3 children. I will call them 1, 1, 1, 2, 1, 3. Let's say 1, 3 has 4 children. I will call them 1, 3, 1, 1, 3, 2, 1, 3, 3, and 1, 3, 4, right? And so on. This is how we label it. So even though I said B is the maximum number of children possible, it is just the maximum number. So it is possible that some nodes may not have B children. They may not have any children also, right? So here in the way I have drawn it, 1 has only 3 children, 1, 1, 1, 2, and 1, 3. And 1, 3 has only 4 children, 1, 3, 1 up to 1, 3, 4. And I'm not talking, so just to avoid clutter, I am not drawing the children of 1, 1 or 2 or 3 or B or whatever, but this is just some part of the tree that I have drawn just to convey what the labeling is, right? So children of the root is 1, 2, 3 up to B. At the second level we have 1, 1, 1, 2 up to 1B, 2, 1, 2, 2 up to 2B, and so on. Finally B1, B2 up to BB. Third level we have 1, 1, 1, 1, 1, 2, and so on up to BBB, right? And so on. And so on, right? And we may not have all these configurations. So for instance, here I don't have, let's say B is 4, we don't have 1, 4, right? Because so what we do is we try out paths in this manner. So we go to 1, 2, 3 up to B, then 1, 1, 1, 2, 1, 3, then 1, 3, 1, 1, 3, 2. So all the levels, all the configurations at a certain level we check in the respective step, right? And whenever we get an accepting configuration, we accept, right? So we will explain how to So the goal, again, let me just state the goal. We have to find in this tree, is there any path that leads to an accept, right? But I don't have access to non-determinism, and I have to do it deterministically. So when I am doing it non-deterministically, I'll automatically or magically I'll be magically able to find the path. But when I am doing deterministically, I'll have to actually go through the paths, right, like in some way, and find out. And that's why we said breadth first search, right? So what we'll do is we will use a 3-tape DTM, right? A 3-tape deterministic Turing machine, right? Where, so this has the input, tape 1 has the input, right? So we want to decide whether a particular input is accepted by a non-deterministic Turing machine, right? So tape 1 has the input, right? Tape 2 we use it for the simulation. So this we will use it for the simulation of the non-deterministic Turing machine, and tape 3 has the counter. So when I say counter, I mean, so we are trying to generate all these things, right? Root, then 1 2 up to B, then all the 2-digit codes, then the 3-digit codes, and so on. So that is generated in the third tape, right? So initially we have the input in tape 1, and we copy the tape 1 content, which is the input to tape 2, right? And in the tape 2 we simulate the non-deterministic Turing machine move, but we do not have non-determinism, so we cannot automatically try out all the possible moves at once. Instead, we will, so let's say if the counter in tape 3 is 1 2 3 1 1 2 something, then we will follow this path. So whenever the first choice for making, whenever the first time that we have to make a choice between let's say multiple successor configuration, the first time we choose the first successor, second time we choose a second successor, third time we choose a third successor, fourth time first successor, fifth time first successor, sixth time second successor, and so on, right? So the counter will guide us which of the non-deterministic choices to exercise, right? And when we see an accepting configuration, we accept. So the counter tells us with which path should take in this tree, right? So counter may tell us to take this path, something, right? So it may tell us to take some path, and we'll follow that path, and finally we accept when we reach an accepting state. And after each time when we reach the end of that path, we increment the counter. So after, let's say 1 2, let's say the counter says 1 2 3 1 1 2 now. In the next time it will say 1 2 3 1 1 3, and next time let's say B is 3 1 2 3 1 2 1, right? Because now there is no 1 1 4. In that case, it will be 1 2 1, and so on. And if there is let's say 1 1 3 is not there. If let's say if that 1 2 3 1 1 does not have the third child, then in which case we will not take that path, because that path itself is not there. We will not accept, we will not reject, but we will just continue with the next option, right? And we reject the computation if, let's say, we come to these level by level, and we reach a level, let's say in this level all paths are rejecting, right? If all the paths in a certain level are rejecting, then we know that every path stops there, right? And in that case we can stop. Otherwise, if there is at least one path continuing, then we'll have to go to the next level, right? So that's the way to simulate a non-deterministic Turing machine using a deterministic Turing machine. So the key thing is that a deterministic Turing machine cannot magically find the path, so it has to manually try to find out the accepting computation from all the possibilities, right? So this actually takes more time, because a non-deterministic Turing machine, if the height is, let's say, h, a non-deterministic Turing machine takes only h time, whereas a deterministic Turing machine now has to traverse this entire tree of height b power h, which is exponential in the height. So we are losing out on time, but as I said earlier, we are not focusing on the resources used. We are only seeing whether the thing that we could the language that we could recognize in a non-deterministic Turing machine, can it be recognized by a deterministic Turing machine? So the answer is yes. We do this process, and if there is an accepting computation path, we will find it. Right. So that's the algorithm by which you can recognize a non-deterministic Turing machine, or not recognize a non-deterministic Turing machine, but if there is a language that is recognized by a non-deterministic Turing machine, you can build an equivalent deterministic Turing machine. Right. So this means that deterministic and non-deterministic Turing machines are equivalent in power in terms of at least the class of languages are recognized. So now we can say that if a language is Turing recognizable, or a language is Turing recognizable if and only if it is recognized by a non-deterministic Turing machine. So, right. So this double-sided arrow means if and only if. And similarly, a language is decidable if and only if it is decided by a non-deterministic Turing machine, because non-deterministic and deterministic Turing machines have the same computation power. If you give me a non-deterministic Turing machine that accepts some strings, rejects some strings, and loops on some strings, I can make a deterministic Turing machine that accepts exactly the same strings, rejects exactly the same strings, and loops on exactly the same strings. So if you are asked to show that some language is Turing recognizable, it is enough to build a non-deterministic Turing machine that recognizes that language. It is not necessary that you have to build a deterministic Turing machine. Building a deterministic Turing machine is also okay, but even a non-deterministic Turing machine is okay. If you have to show that a language is decidable, you can build a non-deterministic decider. Just that one point I want to mention about non-deterministic decider. All the computation paths must halt in a non-deterministic decider, right? So we said that a decider is something where every string gets every string the computation halts. There is no looping. But in a non-deterministic Turing machine, for even one string there are many computation paths. So when do I say a string is decided by a non-deterministic Turing machine? When all the paths are decisive, meaning a string is so if you feed a string into a non-deterministic Turing machine, all the computation paths halt. All the paths either accept or reject. No path loops. No path must loop. Right. So that's the thing. So what we have seen is that a non-deterministic Turing machine, every non-deterministic Turing machine has an equivalent deterministic Turing machine, and hence the class of Turing recognizable languages are the same as the class of languages recognized by a non-deterministic Turing machine, and the class of decidable languages are the same as the class of languages decided by any non-deterministic Turing machine. Finally, I just want to quickly point out one more model which is there in the textbook, which I will not spend much time upon, but I want to just briefly mention it. It is called an enumerator. Okay, so enumerator, unlike a Turing machine, it doesn't accept or reject. It is a machine which has a state control and a work tape. There is no input that is given. Instead, it has an output device which is a printer. Right, so this is an output device. Right, so there is a work tape and a printer. These are the two things. Initially, the tape is blank, no input is given, right? So there is no input, and it works in a different way. It is not like a Turing machine where you give an input, it accepts, rejects. Instead, initially the work tape is blank, and then it starts working. You just switch on the machine, it starts working, and it keeps printing strings in the printer. Okay, so the language recognized by the enumerator is a set of strings that are printed out. Right, it prints out a bunch of strings and maybe an infinite list. So the language recognized by the enumerator is a set of strings printed out. Right, so there is no so either a string is printed or not printed. Right, so it's not like there is no infinite loop kind of situation happening here. However, we don't know what order it prints. So it is possible that a string is not printed now, but it's in an infinite list, it may come later. So there is a theorem which I will just state, which I will not get into the proof of. is that a language is Turing recognizable, right, if there is some enumerator that enumerates it. So when I say enumerates it, it means it prints it out. So a language is Turing recognizable if there is some enumerator that enumerates it. The proof is not that difficult. You can look up the book. So if there is some enumerator enumerating a language, okay, before that it's if and only if, right? It's not if and only if. So if it enumerator enumerates a language, then I can have a Turing machine that kind of simulates the enumerator and check whether the given input string is printed out. So that is one direction of the proof. So the language recognized by the Turing machine will be the same language. The other way is, if there is a Turing machine and you want to build an equivalent enumerator, what you can do is to so basically you want the enumerator to print out all the possible strings that the Turing machine accepts. So you can make the enumerator simulate the Turing machine on all possible strings. But if you try all possible strings in serial order, you can get into an infinite loop. So you have to do it in kind of parallelly. So something similar to the breadth first search approach. So you simulate it for one step together, then two steps, and so on. And any string that is accepted by the Turing machine will eventually be printed out. That's the high level idea. For the details, please have a look at the textbook. And there is also this exercise 3.4, which is the end of the chapter, to give a formal definition for an enumerator. So you can write it like, when I say formal definition, I mean we have the 5 tuple, 6 tuple, and so on. So you can write a formal definition and say what is the transition, etc. So the suggestion is you can consider it to be a 2-tape Turing machine. And the second tape is the printer, and the first tape is the work tape. Right. So we have seen enumerator. We have seen non-deterministic Turing machine and the equivalence of non-deterministic Turing machine. Finally, I just want to say one small point while ending this lecture. So we have seen different models of Turing machine, right? So we have seen deterministic, multi-tape deterministic, and non-deterministic, and all of them seem to have the same computation power. Meaning, if a language is recognized by one model, it is recognized by all the 3 models. If it is decided by one model, it is decided by all the 3 models. So in fact, the thing is that the Turing machine model itself is fairly robust, that these changes, like from determinism to non-determinism, or the increase in the number of tapes, it doesn't really affect what can be recognized or decided, right? So the key things that we want are unlimited memory and unrestricted access to this memory, right? So if you considered a DFA, it had finite memory, it had limited memory. If you had considered an NFA, again it had finite memory. If you consider a PDA, it had a stack which is infinite memory, but it had only restricted access to that stack. So we didn't have unrestricted access to this memory. So, but any model that has unrestricted access to an unlimited memory, along with some reasonable other assumptions, right? So, like, which I don't want to get into. But if a model has unrestricted access to unlimited memory, then it is likely that this model of computation will be equivalent to Turing machines, right? So in that sense, the model of Turing machines is kind of robust. Like even slight changes that you make, like for instance, instead of when we said define Turing machine, we said that the tape is infinite to one side, but not to the other side. There was a left end, but infinity to the right. But instead, what if we had extending to infinity in both sides? Even this is equivalent to the Turing machine model, right? So this is just another example. And I think that is all that I have in lecture number 31, right? So we first said about equivalence of non-deterministic and deterministic Turing machines. We had to simulate a non-deterministic Turing machine with a deterministic Turing machine, right? So we said depth first search does not work, and we tried the breadth first search approach and we formalized it. Right. So in this simulation, we mentioned that we may be losing out on time, right? Because A non-deterministic Turing machine may take only h time to compute this 3, whereas a deterministic Turing machine will take b power h time to try out all the possibilities. But that's okay. We are not bothered about resources now. Perhaps later in the time complexities chapter, we'll see how much resources this takes, right? And then we said that the class of Turing recognizable languages are the class of languages recognized by a non-deterministic Turing machine, right? If and only if. And the class of a language is decidable if and only if it is decided by an NTM. When I say decided by a non-deterministic Turing machine, I want all the strings to halt and all computation paths of all the strings to halt, right? Even for one specific string, I want all the computation paths to halt, either accept or reject. We then saw the enumerator, which was just basically a printer with a work tape. And we said that the languages enumerated by an enumerator is the same as the class of Turing recognizable languages. Finally, conclude by saying that any model of computation which has unlimited memory and unrestricted access to the unlimited memory, they are all equivalent to Turing machines. And I think that's all I have in this lecture number 31. And we'll conclude this chapter number 3 in the next lecture. So see you in the next lecture. Thank you.